You know, the best things in physics are building models and taking a model of something that's kind of complicated and breaking into pieces that aren't so complicated. That's what's so fun. And so let's look at this. This is a little, I don't know what it's called, a chain, a beaded chain, but it's like a string, right? It's a string with mass, and I want to build a model of this. Now, I'm probably not going to add friction and stuff like that. I might do that later, but I just want to model the interaction between these individual particles in this string, and it's going to be awesome. I'm going to use GlowScript vPython. I'm going to show you everything we need to know. This might be a little long, but we know who's going to stop me. You don't have to watch the whole thing, right? Okay, so let's take that string and break it into a bunch of individual masses connected by springs. And honestly, why do we want to do that? Well, a spring, I can calculate the force. And then if I know the force on each little piece, I can model the whole thing. And I can just use some basic physics a bunch of times to get this to work. Okay, so here's my string. So this is my string. It has, in this case, I just put 5 masses in there. And they're connected by springs. The total length of this string slash spring, whatever you want to call it, is L. And the total mass is capital M. Now, the first thing to look at is, okay, what's if the total mass of the string is capital M, then the mass of each one I can call lowercase m, and that's just going to be the total mass, capital M, divided by n, which I'm using n as the number of parts of my string, and I can change that. So in this case, n would be 5. Now, what about the length of each spring? Let's call that S, the distance between the balls, and that's from center to center. And if I do that, one thing you might notice is that there are not n springs here, right? There's n minus 1 because I don't have, I'm not breaking it into, I'm calling n the number of balls, not the number of pieces. So in this case, there's n minus 1 springs. There's only 4 springs. So the length of each one would be the total length divided by n minus 1. Okay, got it. Now, I said springs are great because we can model the spring. Here is a one mass connected to one spring. I can get a vector expression for the force. And that, here it is. So here we have negative k, where k is the spring constant. It's how stiff that spring is. L is the vector from the beginning of the spring to the end of the spring. And it's the vector, okay? And then L0 is the unstretched length of the spring. So L, the magnitude of L, minus L0 is the amount the spring is stretched or compressed. That's important. And then L hat is a unit vector in the direction of L. And that's important, right? Because once I take the magnitude of L, that's a scalar. But I want a vector force. So I need to turn this whole thing back into a vector, so I need L hat. And that's a unit vector in the direction of L. And then that would give me this vector force on the mass F spring, which is a vector. Now, we're going to use that force with, these are the 3 most important things to model the motion of this one single mass. We need the net force, the momentum, and the position. So the net force is just going to be the force due to the spring. That's fine. And then we have the momentum of the mass, and then we have the position of the mass. So how does all of these things related? First, let's look at the momentum principle. This says that the total force on the one object, in this case there's only one force, but we could have more than one, is the change in momentum divided by the change in time. That's important. And then momentum is defined as mass times velocity, and velocity is a vector. The average velocity depends on the position. And in this case, let me point out that I've just had some arbitrary location for where I measure the position from. It could be anything. So the average velocity is the average, we'll get to that in a second, is the change in position over the change in time. So all these things are related. Okay, now what about that spring constant? I guess I should have put this first, but this is important too. So I have the spring constant of the whole thing. If I want this to be a string, a stretchy spring, then the spring constant might be pretty high. But what about when I break that into individual springs to connect all these masses? That's what I need to think about. So here's my my string with the 5 masses and 4 springs. And imagine that I have these 4 springs connected together. I remove the masses to make it easier, and I pull on it with some force F. And I do that, and the whole thing stretches some amount delta S. Then I can say the magnitude of the spring force is the spring constant. I'm using capital K here just to keep it separate from the individual spring constants, times the stretch. This is Hooke's law. Okay. Now let's suppose I look at just one single spring, and it's going to stretch some amount. Now, the thing is, the total stretch is delta S of the whole spring. So each individual spring has to stretch an amount, right? And let's say the whole spring stretched 10 centimeters. Then each spring would stretch 1/4 of that, right? So I have to divide by the number of springs. They all stretch, but they all have the same force on them. So the force is the same. It's a spring force, and it's big K times delta S, where big K is the total spring constant, and that has to be equal to the little spring constant K times the amount of stretch of each little spring, which is delta S over n minus 1. So that means that, did I write it down? Yeah. So the individual spring constant, if I want to model the whole string as one thing, then the individual spring constants would have to be n minus 1 times the whole thing. So they'd have to be stiffer than the whole thing. Okay, that's not super important, but it could be. Now we can go back to the numerical calculation. So this is, how do we deal with these forces that are going to change? Imagine I'm moving these masses around, and each time they move, the springs stretch, and then the springs forces change. So I don't have constant forces. It's not easy to do. So then the key here is to say forces are not constant. But if I break the problem into short time intervals, let's go from time t1 to t2, then during each of these time intervals, I can assume the force is constant. If my time interval is small, then that's fairly reasonable. Now, I'm going to show you what's called the Euler method for numerical calculations. And the idea is to break the problem into a bunch of little bitty steps that are simpler and just do a whole bunch of steps. So I'm going to start off with the momentum principle, solving for the change in momentum. Assume I calculated the force. And then from that, I can say P2 is the momentum at the end of the time interval. That's going to be the momentum at the beginning of the time interval plus the net force times delta T on that object. Now, let me go ahead and say, I'm skipping over some stuff here. I have another video, and I'm going to remember to include that down below that goes through this in more depth. Okay, but I assume that you've already seen that. If not, go look at that video down and then come back to this video. And then once you watch all my videos, you might as well, right? Okay, and then after that, I can use the definition of average velocity to find the position at the end of the time interval. Now here is a trick. Remember, I said V average is the change in position over the change in time, but I'm using P2 over M, which is the velocity at the end of the time interval. That's just a little trick. It works just fine. There are other ways to do numerical calculations that are a little bit more accurate, but this will work. And then I update time. Okay. Now, I also want to make a visual model. I want to actually show everything. And this is the power of VPython GlowScript. So let's start off with this. I'm gonna work this through in real time. But one of the objects, if I start a VPython program, I'm going to be using trinket.io, and I'll include a link down below to my code. If I say sphere is a built-in function, and it actually makes a sphere. A three-dimensional sphere. We can rotate that around. I'm going to show you. The two important properties of that are the position, POS, and that is the vector location of the center of that sphere. And then radius is the radius of that sphere. You can change the color and stuff like that too, but I'm not going to worry about that right now. The other object I'm going to use for the springs connecting the balls is a cylinder. So this is a built-in object in Python, also VPython, not in Python. And it has the position is the location of one end of the cylinder. Axis is a vector from the position to the other end of the cylinder. And then you have the radius. Okay, now here are some other things. I'm going to show you this in real life too. But the other thing that we need to do, if I have, let's say, 5 masses, I could just have 5 masses and do everything manually. But what if I have 20 masses? I don't want to do that manually. So I need to use lists. Here is some, and I have a video below for lists. Okay, so here are the important things for lists. So first, I just have n equals 5. Stuff is an empty list. And so you make an empty list with a square bracket. Now, here's a little cheat that I'm using a list to make a list, but the next in line 5, this says for I in range n. Range n makes a list from 0 to, it makes a list of 5 elements. And so in the next line, it's going to go through, each I is going to be 0, then I is going to be 1, 2, 3, and 4. So I'm going to add that number to my list, and you could use the append function. I like this way better. So I take my list stuff, and it's going to be the old list plus this element, and that adds it on there. And when I print that, I get the list 0, 1, 2, 3, 4. Okay, some important things that we need to think about. How do I address that first item in the list? That's going to be the indices 0. So if I print stuff 0, I get 0. If I print stuff -1 is the last item in the list. And I print that out. Now, I have one other thing. What if I want to go through I want to go through the middle pieces. I don't want to do the first or the end. Well, if I do this for I in range 1 to n-1, n-1 is 4, and this starts at 1. It doesn't start at 0. Okay, normally the indices starts at 0. Then if I print that, I just get 1, 2, 3. I don't get 0 and I don't get 4. Okay, so we're going to use that again. Let me switch over to Python. I'm going to make a list. I'm going to make my string, but I'm not going to model it. And then I'll come back and we'll talk about how to model it. So let's go over to VPython. Okay, I got a head start here. I apologize, but you don't want to see me typing dumb stuff. So let's go over some of the important things here. So first of all, let me make this bigger. Just one complaint about this, and that's better. So I just have some constants here. L is the length of my string spring. It's 20 centimeters. The mass is 100 grams, and the spring constants of the whole thing is 1. And then I'm going to break this into 5 pieces. So then I have my list of objects, balls. It's empty. This left end is where the string starts. I might want to move that later, and so I just put it at 0, 0, 0, and that's fine. Now, ds is how do I step? Oh, this is wrong. ds is, this should be n-1, right? That's what I said, right? I think. Hold on. Where did I do that? Let's see. Yeah, I think that's n-1. Let's just go with it. Well, if it doesn't work, we can fix it. S, oh, that's again n-1. So S is the unstretched length of the spring. So let me just point out the difference between these two. ds is the vector step from one to the next. And L is the same thing. It's just the magnitude of that. Yeah. And then, so R is the radius of the, I didn't think I'd change this. Let me just check real quick. I did work this out beforehand because, it's important to work things out before you do them because you'll make a mistake and then you'll look silly. Let's see. Just let me check right here. Checking. Let's see which one we're on. I think it's this one. No. No, okay, I guess I left it like that. I thought I'd change it. Okay, well let's just keep going. So now I can make my masses. So let's just do that and see what happens. So I'm going to say for I in range, I, not in, I in range, and I'm going to make some mistakes on purpose, okay? Maybe not on purpose. And what I want to do is take that list of balls and add a new ball. So I can say balls equals balls plus. Now, what I want to add a sphere. Now, there's a lot of things here, right? So what is the position of that sphere going to be? First thing, it's going to be POS equals left end plus I times ds. So think about that, right? Left end is where it starts, and then I is going to start off as 0, and then 1, and then 2, and then 3. So, and if I multiply, let's say 2 times ds, it'll be the third ball, the location of the third ball. The radius is going to be equal to r, which I already have. The mass is going to be equal to m divided by n, right? Okay. Now, I can actually do this. I can return it just so we can see. I can add in the momentum. I need the momentum. I'm going to go ahead and set the momentum. P equals vector 0, 0, 0. It starts from rest. And I'm going to do this. F equals vector 0, 0, 0. There's going to be a force, and I'm going to change that, but I want to have a force there. Okay. So let's just run this. Let's save it and run it and see what happens. There. 1, 2, 3, 4, 5. It made my balls. And these are in 3D, so you can zoom around like that. And that's pretty cool. Let's do this. Let's just check and make things work. Working print balls2.pos. I'm sure it works. There. So that's where the location of ball 2. Yay. Now we need to make the connecting lines between them. And in fact, if you had a whole bunch of balls, you don't actually need these springs, but I'm going to make it anyway. So let's make a list for the springs. Springs equals an empty list. And then I'm going to go through and make them. Remember, there's not as many as springs. So, oh, you know what this should be? This is the length, but this should be that, right? Because I was thinking about the length of the spring. That's right. Let's run this again, make sure. Yeah, okay. Because I was thinking about the number of springs, not the length of the spring. No, wait, the length of the spring should be. No, I think that's right. I can't decide. Here, you know what? If you have n equals 100 and you subtract 1, it doesn't matter. Just so you know. So let's go through again and say for I in range n minus 1, right? Because I'm going to have one less spring than I have balls. So I'm just going to do the same thing. Springs equals springs plus a cylinder. The position of the cylinder is going to be equal to POS equals I times ds. Oh, it should be left end. Left end plus I times ds, which is the same as the balls. The axis is going to be ds. And the radius is going to be r. Let's do r divided by 5. I want it skinnier than the balls. And let's run that. Okay, there you go. And rotate that around. That's pretty cool. Now, let's do something even cooler. What if I change this to 10? Check that out. So you can make as many balls as you want. And I think that's really cool. I should probably change the radius should probably be something like, let's see, let's do 5 times n. Yes, that makes it, I don't know if I like that or not. Let's do 3 times n. Why am I playing around with this? It doesn't really matter. But then that way, that when you make more balls, if I change this to 50, it just makes it skinnier, but it makes all the balls. Yeah, that's cool. Okay, now let's change that back to 5. I'm going to save this code. And all I've done is to make the string. Now we need to model the string. So I'm going to switch back over to my presentation, and we're going to talk about how do we model that spring. How do we calculate the forces on it? And because it's kind of complicated. So let me switch over to that, and then we'll come back and start a new program. I want to model the motion of this string. I want everything to move around. So what do we need? What are all the things that we need to do? First, we need to calculate the force on each spring. If I want to use the momentum principle, I need to know the force. Second, I need to in order to calculate, I do need the unstretched length of each spring, which that's constant. And then I need the distance between the balls, which is the either amount that's going to be stretched or compressed. And that actually isn't completely trivial, but the unstretched length is simple. We're just going to call that S. Now, what about the length between the two balls? So here's ball 1 and here's ball 2. So each of those has a vector position, the POS function of the ball. And so the length of the vector is just going to be r2 minus r1, which is going to be equal to the axis of each of the spring. But I need to, as things move around, I need to do that. I need to change those axes. So let's think about the actual string that I have and look at the first ball. So here's those 5 masses in my Python program. And I just want to look at this first mass. Why? Because this mass and the last mass are different. If I have 50 masses in my string, one and the last one are different, right? So that's important. And let's call that first one 0. Let's call the next one 1. But what about the distance between those, the vector L? It's going to be this. It's springs 0 dot axis. Remember, ball 0 and the first spring is spring 0. So that's good. But that's the vector from 0 to 1. This is actually negative L, right? If I think about the L vector connected to mass 0, then that's the negative of that. If it was on the left side, it would work fine. But on the right side, it's going to be negative of that. So then I can calculate the force on this mass, use my normal formula. I use spring 0 dot axis as negative of the L. I have the spring constant, I have the spring length, I have everything I need to know. So I can do that separately. Then I can go over to the last ball and do the exact same thing. The only difference here is that I'm going to use the spring's negative 1 dot axis, which is the last spring, and it's in the right direction. So I don't need to switch it around, right? Because it's attached to that last ball. So the last ball is negative 1, the ball before that's negative 2, which I actually do need to know to calculate the values of the axis for each one. I'm going to use that axis as my length, but I need to calculate that too. What about all the middle balls? So in the middle balls, I actually have 2 springs connected to each middle ball. I have, let's call that ball number I. The ball to the left of that's I minus 1. The ball to the right of that's I plus 1. But I really care about the springs, right? The spring on the left side is going to be spring I minus 1, right? Because if I'm on I, the ball I, which is, if it's ball 1, that's the second ball. The spring on the left is spring 0, which is I minus 1. And the spring on the right is spring I. It's the same number. Okay. But then I have 2 forces on those middle balls. That's why I need to treat those 2 separately. So here's all the things that we need to do, and I put this as one giant list, not even animated. So I'm going to calculate the force on the first ball. Then I'm going to calculate the force on the middle balls. And then I'm going to calculate the force on the last ball. So those are 3 different things. Then I'm going to go through and update the momentum of all the balls. And then I'm going to update the position of all the balls. And then I'm going to update the springs. And then I can repeat the whole thing over and over again. So that's what we need to do. It is going to be complicated, but we can do it. And once we do it with 5 balls, we can do it for 50,000 balls. So let's switch back over to Python and see how this works. Here is the program I just made. Let's copy that. And let's call this model string. Ooh, not there. Model string. String spring. It's a string spring. Or is it a spring string? I'm not sure. So I saved it. And I always like to run things right away just because I never know if something didn't work. Okay. So then I made my models. Everything looks fine. So let's just go through and calculate the forces. I'm not going to put it in a loop yet. I'm just going to say, so I need to, I'm going to call this, I'm going to say this, R11 equals, that's the vector. I need to do this first ball, right? So I need to find this distance between there. So that's just going to be equal to negative, I said it's going to be negative, springs 0, it's the first one, dot axis. Which I don't actually have to do it this way, but I did it anyway. And then I'm going to calculate the force on that first one. So let's scroll this up so you can see. So I'm going to say balls 0, that's my first ball, dot F, and it's going to be equal to negative K times the magnitude of that vector R11, I don't know why I did that, minus S, which is the unstretched length, times the unit vector norm R11. So norm is a built-in function in Python that tells you the unit vector for that vector. Mag is a built-in function that returns the magnitude of that vector. Okay, so I don't have to do that manually. So that's that. That's the force on ball 0. And it should be 0 because nothing's stretched, right? So this distance right there is unstretched. So I think that's good. Now we need to go through and do all of the middle balls. Okay, so let's do this. For I in range 1 to n minus 1. And I'm going to go ahead and print this out, right? Let's just print out the position. Let's print I, and then print balls I.pos, just so we can see that it's doing what we had expected to do. So run that. And it didn't. Gave an error. K is not defined. K, I didn't define that? Okay, I have big K. I just got to go up here. Let's do little k. Oh, below n. So K equals K times n minus 1. That's what we said, right? I think, yep. Okay, there. So it printed out all my balls. It goes, look, I is 1, 2, 3. So I'm just doing ball 1, ball 2, ball 3. I'm not doing the in ones. So that's good. The loop is working correctly. That's good. So now I want to just calculate the force in that. So I actually have 2 forces, right? Let's scroll this up a little bit. I'm not sure why that's doing that. So let's say, maybe this is why. Maybe I need to do this. No. Oops, sorry. That's good. Okay, so I'm going to say balls I equals a dot F, the force, right, is going to be equal to negative K times mag. Now I need the spring on the left. That's going to be springs I minus 1 dot axis. And you got to spell it right. So I found the magnitude of that. I need to actually multiply this by parentheses right there. Minus S. And then I need to multiply that by the unit vector norm springs I minus 1 dot axis. That's the force due to the spring on the left. Now I'm going to say the other one is going to be equal to plus K. And I think I got this thing backwards. So minus K plus, yeah, because it's on the other side, so it's plus. If you get these things backwards, your string will explode, and then you just switch those signs. I do it all the time. I make that mistake all the time. This is going to be the exact same thing, right? Except it's plus, and I'm going to copy this. So it's K. So plus K, and I'm going to just say I, because I is the next spring over. I. There we go. Okay, so that's good. I think that's it. Oh, and then I need to do the last ball. So let's call this, I call this R55, which I don't even know why I did that. I don't have to do this. Let's just say balls -1 dot -1. That, that is the last ball in my sequence. And the force is going to be equal to the same thing, except there's only going to be one of them. And it's going to be negative K, because it's on the right, times the magnitude of the last spring, right? I'm just thinking out loud here. The last spring, so it's going to be springs -1. That's the last spring. Dot axis. I need to take the mag of that. I did. But I need to multiply this whole thing. Minus S times the norm of that. Springs -1 dot axis. You got to spell these things right. You can't be making these mistakes. Okay, I think that's right. Let's run it, and let's just print. Let's do this, just to make sure things are working. let's say for ball in balls. So it's going to go through each one. And I'm going to print out the force. Print ball.f. And they should all be 0 because nothing moved, but that's good. But it'll tell me if there's a syntax error, right? Which there is. Line 30. Balls.f equals negative ball mag springs times I times norm springs I minus 1 dot axis plus, aha, see, K. So let's run that. I guess I should save it and run it. Slow. Okay, I think that's good. Okay, so now what we're going to do is to update the momentum and update the position, update the springs. That's what we need to do. So in order to do that, I'm going to go up here. Where did I start? Right here. And I'm going to make another loop. So I'm going to say, did I put a t in there already? Let's make t equals 0, dt equals 0.01. That's going to be my time step for my numerical calculation. Now let's say while t is less than 3. I'm going to run it for 3 seconds. Rate 100. So if you haven't done this before, rate tells Python, VPython, how many calculations to do per second. And so putting a rate 100 with a time step of 0.01 will make it run in, quote, real time, if it can. Now this thing, all this stuff is in the loop, so I'm going to need to indent it. Indent, 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 indent. I don't need that. I don't need to print the balls anymore. But I do need to go through each ball. And now I know the force in each ball, so I can update the momentum of each ball, right? So I'm going to say ball.p equals ball.p plus ball.f times dt. So it's going to take each force for each ball, multiply it by the time step, add it to the previous momentum of the ball, and make it the new momentum of the ball. So that's my momentum update position step right there. Now I can do the same thing with the position. Ball.pos equals ball.p. And let me point out, this is the brilliance of this, right? If you make the list of the things with an S, and then I make each item as to say this for ball in balls, I can treat it just like a normal thing. It's really, I don't know, I like it. Plus ball.p times dt divided by ball.m. So that went through and updated the momentum of every ball, and it updated the position of every ball. Now I need to update the springs. So let's go to this. For I in range. I did that all the time. I in range 1 to n. Right? Because I want to start at 1. Because I don't like, that way I can say my first spring is, I'm going to have 1 less than I have masses, right? Okay. So let's just do this. Let's say I'm going to update the axis for spring 0. Spring I minus 1, right? I'm going from 1 to n. So I minus 1 is spring 0 at the beginning. So that's right. That's the one on the left. Dot axis. And I did that so that I can, I want to subtract and go back instead of having to, if I had I0, well, I could probably do it either way. So that's going to be ball 1 minus ball 2. So it's going to be balls I dot POS minus balls I minus 1 dot POS. It's the difference in the two balls. Now I also am going to need to, what did balls? Okay, there it goes. I'm also going to need to update the position of the spring. So the position of spring, oh, this is springs. I minus 1 dot POS is going to be the same as the balls I minus 1 dot POS. So if that moves, then it'll move the spring too. I think that's good. And then I just need to update time. Time equals t plus dt. I think this is working. Let's save it. There's a lot of stuff here. And I probably should have said this a while ago. I am not a computer programmer. I am a physicist that does things in weird ways, and so that's fine. I just want you to know that it doesn't have to be perfect. Okay, so nothing's happening there, right? Because I didn't move anything. So let's do this. I wanted to make this thing oscillate back and forth, but I don't want to make it too complicated. So let's just add a small force to this first ball right here. So I'm going to go up here. When I calculate right here, because I want to make things move, let's just add a force plus, it's that spring force plus some tiny force, vector, I'm going to pull it to the left, vector negative 0.0100. So now there's a force on that ball. That ball's going to keep accelerating this way, but that's going to make all these other balls move too. Let's see what happens. It might blow up. Oh no. And look, there's kind of some shaking going on there. I think that looks pretty good. Let's do this. Let's pull it up to 0.002, just a little bit. Okay, see, that's pretty legit. Okay, and I just made, now we have to do one other thing. I forgot. Let's change in to 20. Okay, that's pretty awesome. Oh, look, that thing flipped around. Okay, now, there's a lot of things to add to make this better, right? And I'm not going to do that. You could add a gravitational force to each ball. You could fix the end points of two balls and you could make it a cable. That'd be pretty cool. You can make interactions between so that it can't loop back over itself. I have it able to loop back over itself. You could add air drag, all those things. And I'm going to do those eventually, but I don't want to make this video 5 hours long. So I'm going to stop there, and I'm going to include the links to these codes. I'm going to include the links to numerical calculations and lists and stuff like that. But that's a great place to start. I just want to show you that we can make cool things in Python. And I'll talk to you guys later.